Okay. And so our second session this morning is going to be kicked off by Lisa Upton. Unfortunately, Alan Tidal, who was supposed to talk, has come down with about the flu after visiting Spain last week or 10 days ago or so. Spanish flu. And so I will do my utmost tomorrow in the short talk that I have to channel Alan. And no, I'm going to do my best, I promise. Yeah, I think I'm maybe disruptive enough. All right, so Lisa's going to be talking to us about observing the sun's poles at a new frontier. Take it away, Lisa.
Thanks so much, Scott. Good morning, everyone. I want to start by thanking the organizers for inviting me to talk to you today, especially because this is a topic that I'm very, very excited about. The obtaining direct observations of the coronal structures and the photospheric magnetic fields at the sun's poles represents a new frontier in solar physics. From a polar view, we'll be able to view we'll be able to have, from an overhead view, we'll be able to have to view the seat of the Parker spiral and the interactions of the co-rotating interaction regions. Previous magnetic observations have been strictly from the line of sight position. So if we look at the MDI and the HMI observations seen here, HMI on your right and MDI on your left, we see that they're very, very noisy. And so direct magnetic observations will allow us to clearly see these high latitude magnetic fields really for the first time. And this is really important because these are the seeds to the solar cycle. And so I'm very excited to be at the forefront of this new frontier in solar physics. Now, with surface flux transport models, such as the advective flux transport model, we have an opportunity to kind of simulate the evolution of the magnetic field on the surface of the sun. And it gives us a chance to glimpse what we might expect to see with a magnetic imager from a polar vantage point. These models take in the observed flows and the observed fields and simulate their transport to produce flux maps of the entire sun, butterfly diagrams, polar field plots, etc. And so this is an example of the advective flux transport model in action. We see here where the data is being assimilated, and then on the far side where the advective flux transport is doing its work to simulate the evolution of the magnetic field. We notice that when the polar views are favorable, we are able to assimilate some of the polar regions, but for the most part, we're limited to what the parameters of the surface flux transport provide in order to simulate the evolution of the magnetic flux at the poles. And so there is some question as to how confident are we in these glimpses of what we might see at the poles. Well, we have some ancillary observations that kind of help to validate whether or not we can have faith in these observations. So this is basically I've taken a strip of the magnetic map from aft, focused on the high latitude polarity inversion line, and I've also saturated the magnetic field so we can really accentuate that polarity inversion line to see what the structures are. The red dots that you see here are locations that Nishu Karna measured as being the locations of coronal cavities on the limb. And so on the right-hand side is where the data assimilation is occurring, and on the left-hand side is where the model has been simulating the evolution of the flux for the entire rotation around the far side of the sun. And what we see is as we progress in time, the location of that coronal cavity matches very nicely with our polarity inversion line that we've predicted with the surface flux transport that we've simulated. And we see that cavity very nicely follows the evolution of that polarity inversion line in time. And so that gives us a little bit of confidence in what we're doing. But another really interesting thing that we're able to do with models is that we're not limited by a particular vantage point. And so one of the cool things that we can do is we can turn our orientation and actually look down on the surface, or from a polar view, from a polar vantage point, looking down at the top of the sun to see what we might see. And so this is what I have here. And what you see is that there is negative polarity field at the center of the sun. It's kind of surrounded by a ring of positive polarity. And then around the outer edges, that's where the data assimilation is occurring, where the active regions are being brought into the model. And so what we can do is we can watch this evolution with time and kind of get an idea of what the polar field reversal might look like. And so what we see is that negative polarity field that's concentrated at the high latitudes is being corralled by the positive polarity field that's gradually squeezing it tighter and tighter and canceling as it pushes that flux closer and closer to the pole, until eventually that original polar field is completely canceled, and we're left with an entirely new polar field that matches the new cycle's polar field. And so this is a really interesting way to look at what we might see, this beautiful spiral of the polar field reversal. And so you might ask, how well can we really believe this? So this is another model, or another simulation, or the South Pole reversal. But in addition to just seeing the reversal of the polar field, I've marked the locations of some pseudostreamers that were measured by Laura Rockmiller. And she tracked the location of pseudostreamers, and these are the red and black dots. And you see that the locations of those pseudostreamers very nicely follows the evolution of that polarity inversion line as it's reversing the southern polar field. And so again, this gives us a little bit of confidence in what we're seeing. So I think we might see something like this if we have a polar view, a polar magnetic imager. So this offers a very tantalizing picture of what we might see with the polar magnetic imager. We've previously been limited with our polar observations, but we do have a few limited polar observations, such as the Hinode observations. So here again are the polar views. This time I haven't saturated them quite so much because I wanted to let you see the structure, but not just totally blow you out of the water here. And then I've compared it with these Hinode images. And so these are the same time period. So over here on the left is Hinode at September 2007. And here's what the aft model simulated as being expected. And then on the right-hand side, this is January 2012. Again, the Hinode observations. And then what I've simulated with the aft model. And we see that there's some very striking similarities. You've got a large concentration of flux near the poles. There's lots of magnetic elements populating the area throughout. Whereas in 2012, you have a much more diffuse area. There's not as much magnetic field up there. It tends to be weaker overall. And so it's very nice, very reassuring that these pictures are very similar. But one of the things that was really surprising, and I'm not sure that is quite representative of the model, is the appearance of the kilogauss fields that were observed with Hinode. And so the limited observations that we do have already given us some really surprising results that really challenge our understanding of what's going on. And so we might question, will we be surprised by what we see when we get a mission up to the poles? And I think from looking at these other views, from any other mission that's viewed the poles, from Saturn, Jupiter, Uranus, there's no question there. It's not a matter of will we be surprised. It's more a matter of how will we be surprised. So I'm really, really excited about the concept of a polar mission and what we might be able to do there. I just want to talk a little bit about what we need in a polar mission, and this is just my perspective. You might have some different ideas. I try to be considerate of other areas in solar physics and view what you might need as well. So you might have something to add to this. But I feel like we need a mission that has a polar vantage point above 55 degrees. It should have, as long as we're up there, we need to have some in situ measurements so that we can compare with what our models are saying. We need multi-wavelength spectral heliospheric images. We want to see the entire sun. And these should include Dopplergrams, magnetograms, and even extended coronagraphs. I think we really want to see that seat of the Parker spiral and how those co-rotating interaction regions are interacting with one another. Ideally, we'd like to have something that's at least 1 arcsecond resolution with a cadence of 1 minute. This may be a kind of pie in the moon, really high demand wish list here, but this would be really what we need for helioseismic observations and for doing feature tracking and looking at the fine scale evolution at the poles. Having a polar mission is going to offer us a stereoscopic viewpoint, even if we don't have multiple satellites. If we have just the polar view as well as the line of sight from Earth, that'll give us a chance to do some stereoscopic observations. But I think most importantly, I think what is really, really, really crucial is that we need sustained long-term observations. We've got a few missions that are kind of glimpsing up there for a few days at a time, but we really need something that's going to be able to observe the poles at a very, very long time scale. So I'm talking months to years. So why do we need this? And I was thinking about this, and I feel like, to me personally, the reason why we really need this is because this is what's going to give, these observations are going to give us an opportunity for the first time to have a complete interior to Earth global view of the sun in order to unravel all the sun's global connectivity. How does the magnetic field that's in the interior connect to the surface and then spread out into the solar wind? How does that then produce, then connect to the Parker spiral? And then how does that then connect to us here at Earth and beyond? And so in order to have a true picture of the sun on a global scale, I feel like this is one of the final frontiers, one of the newest frontiers that we could go to really put this picture together. And so, I think that we've already had talks about the interior this morning, very nice talks. Tomorrow, later today and tomorrow, we'll have some talks from the corona. So I'm really going to focus on what this means for the surface observations and how they connect to the interior and to the corona. So this is going to kind of echo a little bit from what we heard earlier today from the interior folks. But the first thing that these measurements will do for us is they'll finally allow us to see what the high latitude meridional flow looks like. The meridional flow is incredibly weak at only a few meters per second, particularly when you go to the poles and it approaches zero. And so this is a very difficult measurement to make. And by the time you take out all the noise, if the noise is on the scale of the velocities, it's really, really hard to get the signal. And so if we have magnetic observations at the poles, then we'll be able to actually finally put to rest whether or not are these polar counter cells that Rudy was talking about earlier, are they really there? Or is this just an artifact of the observations or our line of sight perspective or an inclination of the magnetic fields that we're not correctly accounting for when we do our cosine of rho correction? And so that is really one big question. Let's see. So polar observations will allow us to determine the high latitude structure of the meridional flow. I think another thing that's very interesting and more important in terms of the sun as a star and the global solar cycle progression is what is the nature of the convective pattern at high latitudes? Is the supergranular pattern at high latitudes the same? Or is it slightly different? I'm in particular interested in what the large-scale convective structures look like, because David and I have done measurements by doing feature tracking of the supergranules, and we've got maps that are very much like this. And this is very controversial because it's it's not consistent what the dynamo models have predicted. We don't see very long banana cells extended across the equator. We see that the more distinct feature are these long coherent structures at high latitudes where you've got that high shear from the differential rotation, and rather than these north-south oriented structures. And so I think getting a chance to see what these really interesting features look like at the poles is an exciting prospect to be able to really observe these in high detail at the poles. Moving on to the surface field, I think I cannot iterate enough, and I hope you all agree with me, that we really, really, really need full sun, 360-degree surface maps, surface magnetic field maps. One of the most profound discoveries about the sun is that the sun is magnetic in nature, and we need observations of this fundamental property for the sun in its entirety. These polar observations will allow us to determine how are the kilogauss fields that were observed in Hinode generated. They will give us a view of the far side active regions. Polar observations will allow us to study global interactions such as sympathetic eruptions. It'll allow us to observe the source of the fast solar wind from these coronal holes, and I think that will be really exciting to have a direct head-on view of those. But more importantly, these surface magnetic maps are the boundary condition for all of the other models. What are you going to put in your coronal simulations, your atmospheric models? And so in order to improve on those models, we need to have the most realistic picture we can of the surface of the sun. And additionally, it would be nice if we can better characterize the relationship between the sun's polar magnetic fields and the solar minimum. This has been established as a predictor of the amplitude of the following cycle. We see that that there's a lot of variability across the hemispheres, and so maybe if we have a much cleaner picture of the sun's global polar fields, we'll be able to reconcile why do the different hemispheres have a slightly different property here. And so I think that's going to be really interesting. Finally, the surface structures. A new view of a polar mission will give us a new view of the solar polar structures. This is going to give us an opportunity to do 3D tomographic reconstructions, let us really hone in on where these cool and interesting high latitude features are, such as streamers, pseudo-streamers, coronal cavities, prominences, coronal holes, and really give us a chance to really observe these in fine detail. And in particular, this will give us an opportunity to look at these features over their lifetimes. These are very long-lived structures. And one of the things that stereo showed us was when we used stereo to look at the long-term evolution of active regions, we found that if you scale those active regions as a function of their peak flux, they have this really very standard relationship. And so it'll be really interesting to see what kind of properties we can tease out of these other structures if we have those long-term, extended, lifelong observations of these polar structures. So I just want to finalize my final slide here. Just mention that things are looking good. We've got a lot of very interesting polar mission concepts that are going to be floating around. These are just a couple of the ones that are going to be discussed tomorrow. Solaris, Dan Hassler's going to talk about a constellation of possibly 2 to 4 small satellites with the Jupiter assist, with a combination of remote sensing and in situ instruments. Jeffrey Newmark's going to talk about the Solar Polar Explorer, also with a Jupiter assist, with a 0.5 by 1.5 AU orbit, an inclination of 90 degrees, so it's going to get that direct overhead view of the sun, also with a combination of remote sensing and in situ instruments. But I think the one that I'm most excited about is the Solar Polar Observation Constellation that Tom's been working on. It's just an incredible concept. I think it's got everything that we could possibly want out of a solar polar mission. It's going to have an imaging magnetograph, a coronagraph, in situ instruments. Again, it will have the Jupiter gravity assist. We'll obtain a perihelion distance of approximately 0.5 AU. And it consists of 4 small satellites that are going to be orbiting around the poles. And so if they're juxtaposed with one another, we will essentially have a continuous view of the whole sun in its entirety for a very long period of time. And so this is a really exciting mission concept, and I look forward to tomorrow's speakers and hearing more about these different mission concepts and how we can really revolutionize solar physics with this new frontier of solar physics. Thank you.
Thank you, Lisa. Any questions for Lisa? Questions or comments? Yes.
With one of these polar missions, how does that get us full sun stuff like that? Like I'm imagining something going around the pole. It seems like it would be pretty slow too, going around. So there'd be times when it's on the Earth side versus the back side. So like, how are we trying to get like the whole sun kind of deal?
Well, so for example, with Tom's mission, he's going to have, so if you can imagine, instead of a sphere, let's look at the sun as a circle as we're viewing it from the Earth's line of sight. And so what you would basically have is you would have a satellite here, a satellite here, a satellite here, and a satellite here. And so from those 4 different positions, you're going to have full longitudinal resolution. And yeah, there might be some center to limb variability at the Earth's line of sight, the ring that's perpendicular to our circle. But that will, in essence, give you a full 360 view of the sun.
Thanks, Lisa. Thank you very much.
Thank you.
I think you're proposing a death match for tomorrow.
Yes, a death match. Fight to the end.
Gordon, ready to roll? Okay. Thank you very much.
Yeah. Give you this.
So it's pretty clear that there's a lot to be learned, and a lot that we think we know. But I think we're going to have to raise the bar in terms of understanding and be maybe even a wee bit more speculative about the things that we're going to see. I think Aaron hinted at some stuff, and John Way definitely hinted at some stuff, that there could be some big surprises waiting for us. What is the Chicxulub moment for any of the models or any of the ideas that we have? I think that ties very strongly into what is now becoming known as the Zurbuchen question. What's going to fail straight away? Right. I think there's many Twinian proverbs that could be applied. My very able tech sidekick. Just takes a little bit of time. I hope everybody's logging these Zurbuchen question responses. Capture them all at some point, if we can ever get this done. There we go. All right, and so the second talk in this morning's second session comes from Gordon Petrie of Petrie.
Depends on where in Scotland you're from.
Right.
Petrie's where.
So both Southerners say it different.
Yeah, however you like.
See, if anybody catch that, do we need subtitles? Okay, all right. Gordon's going to give us a talk on towards mapping the sun's polar magnetic field. Take it away.
Thank you very much. So a slight change of Scottish accent. So I'm just going to talk about a couple of efforts I've been making in recent years to map the polar magnetic field. The frustrations and limitations that come from having a single vantage point at or near Earth will become apparent, I think. So I often show this plot. This is a time and latitude plot of the sun's flux distribution, the time on the horizontal axis covering 40 years by now, and the vertical axis being a regular grid in sign latitude with axis labels in latitude. So the poles behave in a very coordinated and organized fashion from cycle to cycle, changing polarity on a 11-year basis. These diagrams are particularly useful for emphasizing the relationship between the low latitude flux and the poles. So you can see the the usual butterfly equatorward migration of the flux emergence as a cycle progresses. And while that's going on, while this fight to the death of the flux at low latitudes occurs, we always get this, this preference of sign in the surviving flux that gets advected or dispersed to the pole. So here, blue means negative in cycle 21, the north. The northern dispersed flux had a preferentially negative polarity. And this, of course, brought about a very large change in the polar field, bringing about its reversal from its previous positive polarity to negative. Of course, we know that this happens every cycle at both poles, opposite polarity in each hemisphere, opposite polarity from one cycle to the next. But the details are very different from cycle to cycle. See that in cycle 21 and 22, the polar reversals are very snappy and businesslike. They were over with in a couple of years, going from strong positive here to strong negative in just a couple of years. Likewise in the south. More recent cycles have been a lot more perplexing in that in the cycle 23 minimum down here, you can see that the dispersed flux from the southern hemispheric flux had a lot less decisive polarity preference. It kind of oscillated from positive to negative to positive to negative to positive to negative. Eventually, over a 5-year period, this polar field could respond and reverse polarity, but it took a surprisingly long time. Meanwhile, the north polar field really very quickly reversed in a couple of years. The recent reversal has been the opposite of that. It's been the south polar field that's been the tidy one, over with again in a couple of years. And it's the northern polar field that's taken ages, since about 2012, and I don't think it's complete yet, or maybe it's just complete. This plot ends in late 2017 because it's based on NSO data, and the SOLAS VSM instrument is not yet operational, having been moved from Tucson to Big Bear. But even at the end of 2017, the progress at the North Pole was not quite complete. Now, I've done a bit of work to make this diagram look the way it is. There is a 27-day average in the time direction, and I've tried to spiff up the poles a bit by various techniques, interpolation, extrapolation, which I won't go into, but here's the unfiltered version. I've removed the 27-day average in time, and I've laid bare the difference between the real flux measurements and the fitted surfaces and so on that I've posed at the poles. But this gives you an idea of, what can still be seen regarding the organization of the flux. The flux polarity biases at the high latitudes still come out. They're just a little bit noisier. And you can see that the real measurements extend pretty far up to high latitudes. We get a good signal to noise with an advantageous B angle, tilt angle. We can get up to about 80 degrees so that the flux density increases monotonically over most of the cycle as we go poleward, pretty much up to 80 degrees. So another thing we can do is compare the full disk measurements of the high latitude fields between very different full disk magnetograph data sets. Here I've got the NSO data set in the top panel. The radial flux density scale plus or minus 10 Gauss. The bottom panel is the Wilcox flux density. It's line of sight, so the scale is somewhat different, and there's also a calibration factor involved here, hence the difference in scales. But qualitatively, the agreement is really good. Because the Wilcox has been observing continuously till the present day, we can go all the way up to very recent past and see that polar fields are approximately balanced at this point, that their reversal is well complete. They're almost symmetrized. There might not be much more happening at the poles. cycle. I don't know that, of course, that's speculation. So the standard theory behind this, we all know, is that the interior fluid dynamics of the sun drives the amplification of a dipole-like solar minimum field to oppositely directed toroidal fields, purely from the differential rotation in the interior. And then another fluid mechanics process, the buoyancy of the strengthened flux, causes these loop-like structures to emerge towards and through the surface. And Coriolis force creates this Joy's law tilt, which is essential for the creation of the poloidal dipole from this process. Enables the cycle to continue on and on between poloidal and toroidal fields. Now, this is based on what we know already about the polar fields, and it would have to be revised profoundly if we were to discover something unexpected in either the helioseismology, these processes here, or the processes that take the flux poleward, take this preferential polarity poleward and reverse the poles. If something unexpected is found in the flow structure here, we would have to change this model a great deal. Also, if we were to discover something weird about what's been described as a top-knot flux distribution at the poles, which I found as this monotonic increased poleward, this is actually undermined by a polar vantage point. There is actually a local minimum of the flux density up there. We'd also have to rethink our ideas. Another piece of the polar field's global influence is the global structure, the global magnetic structure of the corona and heliosphere. There's this famous plot from McComas et al. Of Ulysses data for the solar wind speed in radial coordinates, the speed color-coded by magnetic polarity with red positive and blue negative flux. We have these minimal speeds at low latitudes and fast solar wind at high latitudes. During solar minimum, during solar maximum, it's much more structured. And after polarity reversal, it reverts to this dipolar structure with the polarities reversed. See the correspondence between the solar wind distribution, both the polarity of the IMF and the speed of the solar wind, the correspondence between that and a very simple potential field source surface model. This is just an illustration that the coronal field, which is controlled by the photospheric flux distribution, basically controls the locations of the fast solar wind source and the IMF. So here are more PFSS plots. I've just plotted an annual model over a cycle or two. So the first polarity reversal here took just a couple of years. This is the cycle 22 one. A couple of years to go from one dipolar structure to the next with reverse polarity. Then we had a minimum dipole becoming pronounced. Then the cycle 23 reversal was the messy reversal at the South Pole. So the North Pole reversed in a few years in the south. A long time, about 5 or 6 years. Then we all remember the protracted solar minimum of cycle 23, when it took ages for the corona to settle down into a dipole. It kept having this higher multiple structure until it went really quiet in 2008, 2009. Took on a dipolar structure, and then the recent reversal had a simple south polar reversal, but a very, very complex north polar reversal. Just complete in 2017, we had a dipolar are an almost dipolar corona. Most recent synoptic map from Gong gives us this structure. There's not much activity. The poles are pronounced. This is just a quantitative distillation of what I just said. The dipole dominates the strength of the PFSS model at the outer boundary. This is the axial dipole here. This is the non-axisymmetric dipole. This is the quadrupole. And the other lower order terms are smaller, weaker. Almost everything follows the sunspot cycle, which I've plotted here, except the high order axisymmetric multipoles. So this dominance of the axial dipole over the corona and its dependence on the polar fields is doing that almost alone, axial dipole component. Fix that confidently, of course, we need really good polar field measurements. So that's all low resolution or relatively low resolution full disk data. What about Hinode or high resolution data from Earth? So on the left, we've got Hinode SOT data for the photosphere and FG data for the corona. Some people would say the high photosphere. That's the chromosphere, I should say. And we have SOLAS VSM data for the photosphere and for the chromosphere. You can see we're looking at the same sun. The features line up. Correspondences. See the damage done by the low resolution. Lower signal to noise. We have 1 arcsecond data compared to a fraction of an arcsecond with no seeing. So if I take the SOT data like synoptic data, I transform from disk quantities to latitude and longitude. And I use a recipe devised by Ito et al. Of JAXA. Get the inclination angles. I have 2 solutions, one for each azimuth solution. I grab the more vertical one or the more horizontal one, according to which side of the 45-degree angle it is. So I assume that I have a bimodal inclination angle distribution, either almost all vertical or almost all horizontal. So I do that, then here's what I get. 2013, 2014, 2015, 2016, March of each of these years. The resolution might be suffering here, unfortunately. There's a bit of dynamics as well. But I hope you can see that, and here's the scale here. We've got kilogauss fields. Blue is negative, red positive. So before the reversal, we had mostly red. We had a mostly positive south polar field, very highly concentrated into these facular scale structures of about a kilogauss flux density. Then a year later, it was a mix, positive and negative. A year later, predominantly negative, and 2016, decisively negative. We have these patches all the way to the pole. We can observe to the pole and beyond. But we have a bit of a problem with the effective spatial resolution suffering at the highest latitudes or beyond the pole, so the highest apparent latitude, the extreme edge of the disk. This is just because of the foreshortening. The solar surface area covered by each pixel gets very large, go close to the limb. And I think this is a problem even with the highest resolution data we have for observations from the ecliptic plane, because we will probably not resolve a lot of, we will probably fail to resolve a lot of flux at the highest latitudes. And if we had a polar vantage point, we would find it much easier to resolve stuff here. Show you more what I mean. Made synoptic maps composed mostly of SOLAS VSM line of sight data deprojected into radial flux density. but with the Hinode data just placed at the polar latitudes. So these are the same 4 times as I showed you: March 2013, 2014, 15, 16. We get the same picture of the polar reversal from positive to negative. You can see the features very, very clearly. The signal to noise is really very good. But you see this worrying gap. These worrying gaps appear at the highest latitudes. If I go to the North Pole, which is much weaker, these are September 2013, 14, 15, 16. North Pole was much weaker, so we could only pick up structures at the lowest of the latitudes observed by Hinode. We couldn't pick up much at all near the pole. I think this is just this foreshortening effect. The effect of spatial resolution. Here are polar projections with PFSS models, model field lines overplotted. Left column is Solus 2013, 2014, and this is the Solus and Hinode combo. You can see the facular structures just about. But during the reversal, the facular structures were sort of gathered around the edges of the polar cap, and there were gaps in the middle until the reversal was complete, and then they reappeared. Just a signal vanishing and then reappearing. So the final slide, I just tried to compile a few reasons to take a polar perspective. Made a few of these points already. So we need to pick up the weak flux as well as the strong, and this seems to be very hard to do from the Earth's vantage point, because from Earth we're relying on Stokes Q and U, the linear polarization. It's very hard, it's much harder to get good signal to noise from these measurements than from a line of sight observation, which we could arrange from the pole, from a polar vantage point. This is very important for getting correct the strength and distribution of the polar flux, which would have great knock-on effects for the coronal and heliospheric models, or coronal holes and streamers, and may also force us to rethink flux transport dynamo modeling, because we see something unexpected. On that point, the flux transport pattern could be deduced from a time series of these observations. Again, well, these are usually understood, this flux transport pattern, as the result of an equilibrium between forward meridional flow and supergranular diffusion. And if either of these processes behaves unexpectedly, say we have a counter-cell at the highest latitudes, or we have bizarre, particularly slow diffusion in these very strong facular structures, then that would change the modeling as well. Also, beyond this talk, there are strong motivations to look at EUV images from a polar vantage point to get the polar coronal hole structure correct, absent projection effects, and this would provide a good constraint on the coronal and heliospheric models. Also, 3D reconstruction of coronal loop structure will become possible. Because the structure is optically thin, we can use a second vantage point to deduce some of the 3D structure. And continuous 360 degrees observations of the low latitude loops, the streamer belt, would give us the opportunity to look at sympathetic eruptions occurring at different locations in the corona, and we can see the connections and deduce their cause. Also, finally, I don't know if anyone's mentioned that simply having in situ data accompanying the imagery would help. We would hopefully have the similar success as Ulysses in finding the latitude dependence of the IMF and the plasma parameters, but we would also have imagery to do combined projects as well. Thank you very much for your attention.
Thank you, Gordon. Are there any comments or questions out in the audience? We've got room for one very quick one while Nariaki sets up. I mean, I would look at that and say that there's something canonically different about the evolution of the convection at high latitudes. Right? There's something different about the gathering of magnetic flux at high latitudes versus anywhere else on the disk.
From the facular, structure?
Yeah, the network.
Yeah.
You know, it's different lifetimes, different structure, different coagulation. I mean, if you look at it as an aggregation process.
Yeah, it could be the meridional flow just gathering the flux, and the flux gathering into larger facular structures than is possible at low latitudes, and these larger structures being harder to destroy by the convection, something like that.
Mm-hmm. Yeah, it's hard to tell because, again, you need continuous observations to make that assessment. But from the projections that we have, it looks like there's something canonically different about that evolution up there. And so that's something we need to capture when we think about how we proceed. But thanks again, Gordon, for the talk.
Absolutely.
Very in-depth review.
Thank you.
Is that right?
And carrying on the theme,
You put this back up.
as these guys get ready, of looking at magnetism at high latitudes. Nariaki Nita from Lockheed Martin lab. We'll be talking about polar magnetic fields from Hinode, SOT, the spectral pulmonary comparison. Nariaki, when you're ready.
Yes, I'm ready. Yes.
All right,
yes.
take it away, please.
Okay. As this my Twitter name suggests, I'm more passionate in space weather than traditional solar physics these days, and previously I thought that the multiple stereo missions orbiting in the ecliptic plane may be the solution for space weather predicting improvement. But now I think sub-L1 missions like space weather Diamond, as well as polar missions, are much better than this multiple stereo idea. And my main motivation about dealing with polar field is the magnetic field connection between the sun and the heliosphere. And this one, I try to illustrate this possible problem with the magnetic field connection in this SCP event. This is the famous circumsolar SCP events observed in 2011. And the problem was that the solar active region responsible for this eruption was 60 degrees east behind the east limb. But then at the Earth, the observed SCP time profiles was very quick. And how come these particles come to the Earth so quickly? And I tried to propose that maybe the SCPs came from the South Pole. But that is not supported by any models. Extrapolation based on photospectral magnetic field. And I just plotted this. This shows the magnetic field connection longitude and latitude with the solar wind speed over solar cycle trains 3 and 4. And during solar minimum, at some point, maybe we are connected to high latitude regions, but not beyond 65 degrees poleward. And in solar maximum, we're never connected to high latitude regions. That's really true. And I'd like to ask that question. And interestingly, in this Lario et al. Paper on one SCP event compares the magnetic field connection to stereo B Earth, stereo A, and for stereo B, is different methods, PFSS, mass model at the predictive science. And one point, this is the really outlier. At the latitude, very high latitude was connected, as shown by WSA Enlil. So maybe this shows some uncertainty about our knowledge of magnetic field connection. But what I'm doing is different reasons. compared with Earth observing, we will never have so dense observing coverage. So in most of heliosphere, we have to rely on models. And these models, heliospheric models, 3D simulation models, rely on photospheric magnetic field, typically in the form of synoptic maps. But from the Earth, instantaneously, only 1/3 of the surface is observed, because half is backside, 1/6 is too close to the limb. So maybe there is no decent magnetic field measurement. And the models often fail, as you know. And maybe model has problem, but maybe we can blame the input magnetograms. Often, in this case, the gong magnetograms are used. And there is a O2R program run by Tom Berger, which is recently awarded. One task is to evaluate the gong magnetograms for polar regions using high-resolution Ionosphere data, and we are tasked to do it. And polar magnetic field is very difficult to measure, extremely hard to measure from the ecliptic observations, as many people said. And the sun is tilted only by 7.25 degrees, and only March and September we see either South Pole or North Pole. But other times it's very hard, and only high-resolution vector measurements with good sensitivity is useful information. This diagram shows the advantage of Hinode observations, but several observatories, including GONG, doesn't have a vector field measurement, produce polar field measurement from line of sight measurements and applying cosine mu. This is because vector field measurement is intrinsically noisy. People say the noise level is 100 Gauss instead of 10 Gauss for longitudinal measurement. And others rely on flux transport models. And in recent years, I was really amazed by the progress of numerical models. I previously didn't trust any of these things, but now I'm really looking at those things. But based on those models, people say that the polar field is too weak, and introduce some arbitrary fudge factor, and maybe the magic number is 2, as I was told. I don't know. But this example shows this LASCO observation, simulated the LASCO data using the original GONG data. But if you increase the polar field by factor 2, it becomes closer to the observations. And this is rather complicated, but it shows the deflection of EUV waves, which was realized only when the polar field is doubled. And this comes from the Michigan AWESOME simulation called AWESOME. And then just talking about Hinode programs to observe, special programs to observe polar field. There are 2 programs called HOP81 and HOP206. And HOP81 has multiple programs, but the DAY1 is full resolution and wide field of view observing with a long exposure, deep exposure. And the DAY3 too may be observed in a other pole or repeat, but a half resolution, meaning 2x2. And HOP206 is a 2x2, but it does every 3 days to cover the entire longitude. And the papers on polar field observed by Ionosphere, and the Tsuneta et al. Paper first said that patch is a strong field, but it's just a 1-day observation. And Ito et al. Just 1-day observation for polar regions compared polar region with a quiescent region. And the Shiota et al. Talked about the polar field reversal to solar cycle 24, I'm sorry. And the Petri et al. Tried to make the hybrid synoptic maps using Solis and Hinode, and he already showed those maps between 2013 and 2016. And I said the HOP206 is to do a panoramic view Is that the right pronunciation? Anyway, to cover the whole longitude by observing every 3 days or something for 1 week, 2 weeks. And but here, I just use day 1 of HOP 81. I said the full resolution, deep exposure, and 16 of those maps for 8 each for North and South Pole after SDO launch. And I'm not a specialist of Stokes polarimetry, so just take it easy. You use the HAO Merlin product, level 2 data. Maybe this is a problem. And the disambiguation, you just follow the Ito et al. Description, but assume that the polar field is, at least the strong field is more vertical. So choose one of the 180 degrees, choose the one that makes a field more radial. That is called the radial acute angle method. And maybe that is not too bad because enhanced field tends to be more radial. And I just plotted the field strength and filling factor and cosine inclination. And they use the world coordinate system to make a polar map. But just to do some sanity check to compare the result with Sneda et al. And this is the Sneda et al. And and this is mine. It's quite similar. So, but there is a difference, and the difference may be due to the different inversion, because these Japanese results are consistently use the inversion code called Milos. Milos is also Milne-Eddington approximation, but it treats scatter light with a better sampling, and people claim that it's better for weak field regions, including polar regions. So maybe there are differences. And just show you some the evolution of polar regions between on South Pole and North Pole separately. And this shows that South Pole between 2011 and 14, and started from relatively strong positive field and slow reversal and became, at this point it's not reversed yet, but then between 2015 and 16 there was a big emergence of negative field, and that is up to now, that continues up to now. But the north field actually started the reversal earlier, and the predominantly negative, and by 2013 it was kind of balanced between positive and negative. And it fairly slow reversal after that, but now it's dominated by positive polarity. So I did this analysis up to 2018 March. And this is consistent with what we see in the HMI observation, but this comes from a line of sight measurement. The North Pole started the reversal earlier, but it's fairly slow reversal. And South Pole was late starting the reversal, but it became fairly quick reversal around the 2015-16 period. And this is, as I said, line of sight measurements, but Hinode observations, lots of problems. For example, the pointing information, it's very hard to get that information from Hinode observation alone. So I have to use the HMI data. And by doing that, use the HMI for our pointing calibration. And I also analyze the HMI data and using the vector data, using this data set called HMI B720 7/22 every 12 minutes, the vector, full disk vector data. And I compare I just also made polar projected maps from HMI. You probably don't see many of these like Hinode, like this, but overall, SP strong magnetic field patches are seen also in HMI data. So this was really my surprise. And I just went on and made a movie like this. You probably haven't seen this kind of movie, right? And I think this shows a lot of information about the evolution of, original evolution of these small patches. And I'm trying to use this more extensively to understand how the polar field evolved. Of course, there is a problem. Yeah, I'll show you later. And this one shows also polar projected image movie, the AIA 1600 also wavelengths to see that there is no persistent feature just around the pole. So the lack of strong field or persistent magnetic field near the polar region may not be just a result of the losing spatial resolution there. So maybe intrinsically there's nothing there on long term. And this shows us, scatter light corrected HMI data. When I showed these movies at the Hinode 12 meeting, Amy Norton approached me suggesting that I should use a better HMI product using a better scatter light correction using with a point spread function. But it turned out that there's some artificial noisier and some artificial patterns which should be sorted out. Okay, so I'm going to conclusions. So magnetic field measurement of the polar regions is very crucial, but it's hard to measure. And Hinode SOT produced excellent data, but in order to make the best use of it, maybe we should be more careful about different inversion and disambiguation. And maybe HAO people can help us, I don't know. and to my surprise, full disk vector magnetograms from SDO HMI give the landscape of magnetic field in polar regions comparable to SP. And they, with a constant cadence, they can be used to study the evolution and the original patches of enhanced radial field. And the AI data shows that there's no resident component sitting at the pole. But lastly, we should acknowledge that these advanced data there's only very limited measurements, and that a comprehensive view of the polar region needs clusters of satellites in polar or inclination orbit. That's really what I want to say. This is still kind of a consolation prize, and this shows. Now I show the North Pole and South Pole from HMI together, and this is from March. So you see better coverage for South Pole, right? But North Pole you don't see much, and in June, both are not so good, very close to the pole. And in September, you see, patterns more close to the North Pole than the South Pole is kind of left out. So in order to observe both poles, this is not good. Okay?
Thanks, Nariaki. I think we have time for one question. Dean, are you ready to get set up? Yes, Lisa. You please use the mic, Lisa.
So my question, I really liked your polar views there, especially there at the end. You showed the 1600 angstrom view. What phase of the solar cycle was that during solar maximum, solar minimum? Because it looked like you were showing 2015.
About the crucial period that Laurel, the last name? Laurel.
Rockmiller?
Yeah, Rockmiller. Yeah.
Okay.
She showed a reversal like in the 2015-ish period. This is about that period.
Well, my concern was that if you're looking at that time period, that's at a time that's near solar cycle minimum, and so the polar fields are going to be very, very weak. I'd be more interested to see if you saw any kind of structure in AIA near when the polar fields were much stronger.
Yes, I agree with you. And I'm making these movies.
Ah, wonderful. Thank you very much.
So we will screen those all evening for all 2.5 evenings that we have. So get working on those beautiful movies. Yeah, those are pretty spectacular. So I think the hint you have there is that it's not just the snapshots. Temporal evolution is critically important. I've looked at stuff that I'll try and show tomorrow also, not using magnetic fields but other tracers, and these tracers you can see stuff to the poles, but the evolution's very erratic. But I think this was a pretty nice segue if talking about what happens when you have unipolar flux distributed over a large area or a coronal hole, and how coronal holes have evolved over the last cycle, or even recently. It's up. And so, Dean, are you ready?
Oh no.
Will be the man that stands between us and lunch.
Oh man, you stole my joke.
But
Right.
we talk to us about areas and shapes of polar coronal holes. Take it away.
Right. So I'm going to talk about something I've been working on with a number of students and other research people for over a decade now, and that is trying to measure the area and the lifetime of the polar coronal holes. And I have some reasons for doing that. For one, we've seen from solar eclipses that the poles of the sun vary differently than the rest of the sun. So we already had clues that there was something special about the poles. What can we measure? So I'm not going to reproduce Life's talk because I don't have to. And there was another one I don't have to. So I was able to skip a half dozen slides. Besides the polar magnetic field, which has been measured somewhat continuously since the mid-60s, pretty well since the mid-70s, and we have sporadic measurements back into the 50s and possibly earlier. We have other measurements, polar crown filament. You can see that in H-alpha, and people have tracked those for quite a while. We have the opening angle of the polar cap. We're going to talk about that in a minute. And then we have the areas of the polar coronal holes. Now, that last one only becomes useful when we put EUV imagers up into orbit. And we can actually watch the development and the decay of these features. Before that, they were ephemeral observations, but it's really with the launch of SOHO and EIT, and in the follow-on mission, STO, that allow us to measure these as a function of time. But let me tell you why I did this. I work with a guy named Ken Shatton on predicting the solar cycle, and we used the polar magnetic field as our precursor. A weak solar field now means a stronger activity in the next cycle. You would like to, since we don't have polar field measurements, well-resolved polar field measurements only exist since the 70s, and I know that Mount Wilson's trying to get better so we can extend it back another cycle. What other things do we have that are long-term? And one is the shape of the corona at a total solar eclipse. And so another co-worker of Ken's, Layden, did quite an in-depth survey of total solar eclipse photographs and tried to measure the polar cap area. So here the polar cap would be, does this show up? Yes. So you're trying to distinguish between this helmet streamer and that polar cap, and this is last August's eclipse. And you measure the one on this side, on that side of the sun. Oh, come on, there you go. Then you measure that side, and you measure this one. So you get 4 points, and then you make an angle over the North Pole, an angle over the South Pole, and you plot it up. So don't look at the 2 red points. Okay, you're looking at the red points? Okay, look at the others. Those are the original points Layden put up, and he gave a fit, which is that dashed line that relates the activity in the next cycle to the area, the opening angle in this case, of the polar coronal hole. And I said, that's pretty cool. It's been a number of years, 2 solar cycles since he did the measurements. I'll go get some of Druckmüller's eclipse photographs, which are actually pretty cool to work with, and I'll put those 2 red points in. Now all of a sudden that linear fit has become a parabola. It says that the polar coronal hole, as measured with this technique, is inconsistent as a predictor of the upcoming solar activity. So I said, well, what else can I do to try and extend that? So we came up with a couple of different ideas. You can count black pixels on synoptic maps. That was unsatisfactory. We'll talk about that in a minute. You can do what we call perimeter tracing, where you essentially do those 2 points at the North Pole, 2 points at the South Pole, and you can watch the sun rotate, because with the EUV images, you get the images continually. You don't have to worry about waiting for a relatively rare total solar eclipse. And you can also do the magnetic inflection point. You take a magnetic synoptic map, you do a longitudinal average, you plot that up, and you look for where the field first changes sign, starting from one pole and headed towards the equator, and you repeat that for the other side. And that's another estimate of the area of the coronal hole, polar coronal hole. And they, believe it or not, after many years of work, they all tend to agree. Actually, they all look okay. They vary in detail, especially near solar maximum, but all the methods tend to agree. Here's a synoptic map. So you're just going to count black things, okay? And that'll give you the area of the coronal holes. We do it a little bit more sophisticated than that, but in general, that's the idea. What's the problem? Problem is the wall effect. I am looking at the area of the polar coronal hole, and I am looking at something that's far into the pole, and I have corona that comes out and covers up the closest part of it. I called out the wall effect. I drew up a really nice, colorful diagram, and then I was told I had to show them here. Okay, so that's what it looks like. I'm looking at the yellow thing is the corona. I have my line of sight from wherever I am, and I'm looking, and it's obvious that the polar coronal hole area is underestimated by this technique because the limiting latitude has been moved poleward. If the rotation axis is tilted towards me, is that right? No, tilted away from me, then I get an even smaller area because the same size corona is able to block a larger fraction of the polar coronal hole. And if it rotation axis comes towards me, I get a slightly smaller or a slightly larger hole. And so I get an annual fluctuation built in. On top of that, we have the B0 problem, where the sun's actually moving around, and if your ephemeris is off and you're looking at these high tangent lines, you have that issue. So to get around this, we developed a thing called perimeter tracing. And basically, we're going to do what we just did for that solar eclipse. 2 points in the north, 2 points in the south. We're going to do some fancy math, open and morphological close, all kinds of nice stuff to try and isolate those 2 points. Let's compare the result from perimeter tracking to that of the synoptic map. And when I say they agree in general, but disagree in detail, this is what I mean. They actually agree pretty well in this area over here, kind of near solar minimum. They disagree during solar maximum, and they tend to agree well back at solar minimum. But they disagree at solar maximum. That's because solar maximum, the polar coronal hole, is actually poorly defined, and it probably isn't a useful thing there. But the magnetic thing is actually kind of cool. If I just take the synoptic maps, radial synoptic maps put out by HMI, and find the first point where the longitudinally averaged magnetic field changes sign, and then just plot that up. Here's an area, I think. Yeah, the fractional area. It's pretty cool. You actually see the flux. I cannot see the mouse over here. Here's the latest one. Here is the south pole, the red, coming down and kind of stabilizing. You can actually see the stuff coming down and forming the polar coronal hole. This is a nice method. It also has some problems that the north is which are the plus signs. The north is just a mess. You really can't learn anything about the North Polar Hole yet. All right. Michael Kirk will talk a little bit more about these. We've actually been using these as a set point to try and do some advanced statistical methods, and now even moving into the area of machine learning to try and figure out how to better measure the polar coronal hole. But looking down on the poles would certainly be a lot easier. Okay, I mean, basically what we're doing is we're sitting here looking at the worst possible place on the sun and trying to figure out what's going on as a function of time as the corona intrudes and retracts, as it enlarges and gets smaller, and then you have the B0 effect, and it's just everything you can think of can go wrong with the measurement of the polar coronal hole area. So looking down on it would be a big advantage. So the formation, maintenance, and destruction of the solar polar coronal hole would be a very good mission goal. My conclusions, maybe we should rush to the poles, but really, just use it for a fast spacecraft to the poles. All right, thanks. You can ask questions, or you can go to lunch.
Thanks, Dean. And I guess if we're rushing to the polls, we should always just back a Norwegian, because the
what?
Brits always get there second.
Yeah.
Right?
Whatever.
So, no Norwegians in the room. Sarah?
Of the polar coronal holes, what is your answer to Zubuk's question? You talked about formation, evolution. Those are longer term. What do you think is the fast 3-4 day thing you might discover?
So I was thinking about that, and I was looking at Lisa's plot, where she showed how the flux moved into the pole. And I think just looking at how long it takes rotations to build up that image, and you compare that against a snapshot, and you wouldn't see the discontinuity at the terminator, or whatever you would call the line as you roll around on the rotations. And I think that would be nice to be able to just compare, especially as a movie. I don't do stills anymore. Remember, we're doing the sun in time, and you would have a movie that shows that line kind of clocking around, and then you would have another one that just shows the sun evolving. And I think that would be the cool thing to do. Trouble is, it's going to take you a month. It's not a 3-day kind of, it's not your first light kind of image. It's your first rotation kind of image. But that's what I would think. Do a movie. People like movies.
Dean, you should not forget that the coronal holes were first observed in the green line by Waldmeyer.
I had that in the thing.
So he even coined the concept coronal hole. That was his word. But that goes back to the 1940s.
The 34, I believe, is when the observation started.
Yeah. So our knowledge of coronal holes did not start with Skylab.
The trouble with the 5303 images is that the polar coronal hole goes to the equator in those images. Now, the polar coronal holes, during solar minimum, the polar coronal hole will grow essentially to the equator. The polar coronal hole is very large compared to what you see in the EUV. And we pointed, it was in one of your papers. We have these very nice limb synoptic maps that show that the 5303 line's emission is not a good tracer of what's going on near solar minimum. So we have looked at that. That was one of our ideas, is we would calibrate the EIT and SDO images against 5303, and that would allow us to go back into the 30s. But when we've done that, they're just too big from the 5303. We have not been able to calibrate that issue out. So we have looked at them.
And of course, that's one of the other challenges, is what comes between the green line and lunch.
Another question?
All right. Well, thank you. And thanks, Dean. And thanks also to all this morning's speakers. Hopefully you will be priming questions for them, as they will be asked to come back up to the stage later on for open discussion. But now please go for lunch, and we'll reconvene at 1:30 prompt to kick off this afternoon's discussions. Thanks. Absolutely.